A silent void erupts into a cosmic firestorm of newborn stars when galaxies collide. We are made of star stuff, as Carl Sagan said, and this star stuff is forged in the universe's most violent events. Why should we care about processes that take billions of years? They hold the keys to our own origins and the ultimate fate of galaxies. By the end of this journey, you will understand how the chaos of colliding galaxies builds the very elements of life. We will uncover how gravity orchestrates these slow-motion dances and what triggers the sudden, brilliant birth of millions of stars. How does a gentle pull in space ignite a stellar explosion? Two immense spirals of stars begin a slow, gravitational embrace across millions of light-years. This is not a chaotic crash, but a stately dance choreographed by the universe's most fundamental force. Gravity orchestrates every movement, pulling these colossal structures together over timescales that dwarf human history. While the cosmic scale can feel incomprehensible, these events are governed by the same physical laws we experience on Earth, just amplified to an almost unimaginable degree. Each galaxy is embedded within a vast, invisible halo of dark matter, a mysterious substance that exerts a gravitational pull without emitting any light. It is this unseen dark matter that first locks the galaxies in their fateful trajectory, guiding them closer with each passing eon. The outcome of this celestial dance hinges on speed. When galaxies approach each other at relatively slow velocities, they have time to interact dramatically, their gravitational fields entwining and distorting their classic spiral shapes. These slow-motion encounters can ultimately lead to a complete merger, often resulting in a new, featureless elliptical galaxy, a quiet giant where star formation has largely ceased. Our own Milky Way is not a passive observer of this cosmic process. It is destined to collide with the neighboring Andromeda galaxy billions of years from now, a future merger that will utterly reshape our night sky. We can see this process playing out elsewhere in the cosmos. Look at the Antennae galaxies, for instance, where two spirals have already passed through each other. Immense tidal forces, much like the pull of the moon on Earth's oceans but on a galactic scale, have drawn out long, streaming arcs of gas and dust, resembling the antennae of an insect. It is within these violently disturbed clouds, this cosmic wreckage, that the stage is set for the next act. How does this gravitational chaos become the cradle for new suns? The answer lies in the turbulence within those vast, scattered reservoirs of raw material. Earth's entire history could fill a calendar year, yet humanity's entire story would blink into existence in the final seconds of December 31st. This is the staggering perspective of deep time, a framework not of years or centuries, but of billions of years. It is the only timescale vast enough to contain the life cycle of galaxies. The concept echoes the insight of geologist James Hutton, who saw in Earth's rock cycles no vestige of a beginning, no prospect of an end. We now apply that same profound lens to the cosmos, where the slow dance of colliding galaxies unfolds over epochs that defy human imagination. To witness these events, we rely on the ultimate time machine, the telescope. When we peer at a galaxy millions or billions of light years away, we are not seeing it as it is today, but as it was when that ancient light began its journey to us. We are literally looking into the past. This allows astronomers to create a cosmic flipbook of galactic collisions, observing different systems caught in various stages of their gravitational tango. The key to measuring these vast distances and ages is redshift, the stretching of light waves as the universe expands. Think of the sound of a passing ambulance siren, how its pitch drops as it moves away. Light from receding galaxies behaves similarly, shifting toward the red end of the spectrum. By measuring this redshift, we can calculate not only how far away a galaxy is, but also how long its light has traveled, letting us pin a date on our cosmic observations. We can peer even further back to the faint afterglow of the Big Bang itself, the cosmic microwave background radiation. This ancient echo provides a foundational timestamp for the entire universe, confirming its immense age of nearly 14 billion years. A galaxy like the tadpole with its long, stellar tail is a perfect example. We see it not as a completed merger, but as a snapshot of a violent encounter that happened hundreds of millions of years ago. Its distorted shape tells a story of gravitational chaos that is still unfolding from our distant viewpoint. To think in deep time is to fundamentally shift our relationship with the cosmos. It reminds us that the universe writes its grandest narratives in the slow, patient ink of epochs. This expansive perspective is crucial, for it prepares us to understand the specific, powerful triggers that awaken stellar nurseries within these long-term cosmic dramas. A serene galactic disk spinning in quiet equilibrium for eons is suddenly thrown into chaos by an invisible hand. The gentle, persistent tug of gravity from a passing galaxy begins to warp and twist the very fabric of this stellar island. It is this initial gravitational disturbance, this cosmic push, that ignites the entire process. As Isaac Newton once reflected on calculating the motion of heavenly bodies, even he might have been humbled by the creative madness that gravity unleashes in these collisions. The key lies in compression. Within every galaxy drift immense cold clouds of molecular gas, the raw material for building stars. They exist in a fragile balance where internal gas pressure just barely resists the cloud's own inward pull of gravity. Then the collision happens, the tidal forces from the intruding galaxy, immense gravitational pulls that stretch and squeeze matter, act like a cosmic fist. They violently compress these vast gas clouds, squeezing them from all sides. This squeezing dramatically increases the density of the gas. At a critical threshold, everything changes. The cloud's own self-gravity, now supercharged by the external pressure, suddenly overwhelms the internal gas pressure that was holding it up. The balance shatters, and the cloud begins a catastrophic collapse under its own weight. Astronomers have a way to predict this moment of instability, a concept known as the tumor stability criterion. In simple terms, it describes the conditions under which a thin, rotating disk of gas becomes unstable to these gravitational perturbations. When the forces of gravity, pressure, and rotational shear fall out of their delicate balance, the disk can no longer maintain its structure. It fragments. We see this principle in action when we look at systems like the Mice galaxies, two spirals locked in a tight embrace. Detailed computer simulations of their interaction show clear gravitational perturbations, waves of density that ripple through their gas disks. These waves create pockets where gas piles up, forming dense knots and filamentary structures. Each of these knots is a potential stellar nursery, a region where gravity has taken firm hold and collapse is inevitable. Adding to this turmoil are powerful shock waves, rippling through the interstellar medium like sonic booms on a cosmic scale. These waves slam into gas clouds, delivering another powerful dose of compression and further catalyzing the collapse. So, a gentle gravitational pull becomes a star-making factory through this fundamental act of violence. It takes a vast, diffuse cloud and concentrates it, triggering a chain reaction that gravity will see through to its brilliant conclusion. But this initial gravitational squeeze is only the first act. the true storm of star birth requires another, even more potent ingredient to fully awaken. That gentle gravitational squeeze acts like a cosmic trigger, but the true firestorm requires fuel. Within a serene, undisturbed galaxy, interstellar gas is spread thin, a diffuse haze drifting between the stars. It is a quiet, almost dormant reservoir, but when galaxies collide, this gas is violently funneled and crushed. It is forced into incredibly dense pockets, cosmic pressure cookers where the very conditions for star formation are ignited. Research from the Hubble Space Telescope confirms that these galactic collisions can boost star formation rates by factors of 10 or more. What does that physics look like up close? Vast clouds of gas, each light years across, are sent on collision courses. When they slam into one another, they lose their angular momentum, the spin that might otherwise keep them stable. Stripped of this rotational support, they can no longer resist the relentless inward pull of their own gravity. The clouds begin a catastrophic collapse, fragmenting into clumps that will become protostellar cores, the seeds of new suns. Astronomers describe the precise moment of collapse using a concept called the gene's mass. In simple terms, it is the critical mass a cloud of gas must reach before its self-gravity overcomes the internal pressure trying to keep it puffed up. When external forces from a galactic collision compress the gas, they dramatically increase its density, effectively lowering the required gene's mass. This makes it far easier for smaller regions within the cloud to cross that threshold and begin their gravitational fall. We cannot always see this process directly with visible light, as these stellar nurseries are often shrouded in thick, opaque dust. But we can peer through the veil with infrared telescopes. The dust, heated by the fledgling stars buried within, glows brightly in infrared light. These infrared bright regions are the telltale signatures of hidden star birth on a monumental scale. Look at the merging galaxy known as ARP 220. It is a spectacular example of this extreme physics in action. The collision has funneled an immense amount of gas into its core, creating a region of unbelievable density. This has triggered a starburst, a furious episode of star creation where thousands of new stars may be born every single year, a rate hundreds of times greater than in our own placid Milky Way. So, what specific conditions transform a cold, dark cloud into a brilliant new star? It is this intense compression, this cosmic forging process that sets the stage. But the birth of a star is not a quiet emergence. It is a violent, tumultuous event that unleashes powerful forces capable of both creating and destroying the very material that surrounds it. A galaxy can ignite, transforming its quiet spiral arms into a brilliant firestorm of newborn suns. This is the spectacular reality of a starburst galaxy, a system undergoing an episode of ferociously rapid star formation. As astronomer Deborah Elmer-Green observed, starbursts are the universe's way of recycling material on a grand scale. Galactic collisions are the primary architects of this cosmic recycling, funneling immense reservoirs of gas into dense central regions and creating the perfect conditions for a stellar baby boom. The characteristics of these events are unmistakable. The rate of supernova, the colossal explosions that mark the deaths of massive stars, skyrockets. The surrounding gas, heated and ionized by the intense ultraviolet light from all these new stars, glows with powerful, specific emission lines that act as a fingerprint for rampant star birth. These starbursts are incredibly intense, but they are also fleeting on a cosmic scale. They typically last for only 10 to 100 million years, a brief, brilliant flash in the multi-billion-year life of a galaxy. Yet in that short time, they fundamentally reshape their home. The frequent supernovas seed the galaxy with heavy elements or metals, enriching the interstellar medium and ensuring that the next generation of stars and planets will be built from more complex ingredients. A perfect example is the Cigar Galaxy, known as M82. Its recent close encounter with its larger neighbor, M81, triggered a fierce starburst in its core. Observations in X-ray and radio wavelengths reveal a galaxy blowing vast bubbles of hot gas out into space, a direct result of the combined winds from thousands of massive stars and the relentless shock waves from countless supernovae. This ferocious activity leads us to a pivotal question. Why do these brilliant bursts of creation inevitably fade? The answer is one of simple cosmic economics. A starburst galaxy is living far beyond its means, consuming its vast gas reserves at a breakneck pace. It is a fire that burns so brightly it consumes its own fuel, leading to a relatively swift decline. This intense, self-limiting nature of starbursts forces us to look closer at the kinds of stars forged in such a frantic and chaotic environment. What is the stellar population born from this turmoil, and how does it differ from the quiet, steady star formation we see in a galaxy like our own? Within the stormy seas of colliding gas clouds, chaos itself becomes a cosmic architect. Turbulence, a violent and unpredictable churning of matter, carves out the specific conditions needed for the universe's most spectacular stars to be born. This is not a gentle process. It is a supersonic maelstrom where shock waves, rippling outward from cloud collisions and supernova blasts, act like cosmic sculptors. They compress the gas into incredibly dense knots and long, thin filaments, structures where gravity can gain a decisive foothold. Observations from the ALMA telescope have revealed a crucial insight into this turbulent environment. While it can prevent the formation of smaller, sun-like stars by keeping gas too stirred up to coalesce quietly, turbulence actually enhances the birth of high-mass stars. It does this by creating those intense, high-density regions where collapse happens rapidly and on a grand scale. The mechanics are both violent and precise. Supersonic turbulence, where gas moves faster than the speed of sound within it, creates a complex web of intersecting shock fronts. Think of it like the chaotic, crisscrossing waves in a storm-tossed ocean where powerful currents collide. At the boundaries where these shock fronts meet, gas is piled up and squeezed with tremendous force. This sudden compression can trigger gravitational instability in a cloud, pushing it over the edge into collapse far more quickly than in a calm environment. The result is a dramatic shift in the kinds of stars being forged. In a quiet galaxy like our Milky Way, star formation follows a standard distribution, with many more low-mass stars produced than high-mass ones. But in the frenzy of a galactic collision, this initial mass function is skewed. The scale tips, and a greater proportion of the new stars are born as heavyweights. We can see this principle written across the sky in the Antennae galaxies. Hubble Space Telescope images pinpoint brilliant, blue clusters of stars forming precisely within regions that have been shocked and compressed by the ongoing collision. These are not nurseries for gentle suns, but factories for stellar titans. How does this turbulent environment decide a star's ultimate fate? It essentially sets the mass scale from the very beginning. By creating denser seeds for collapse, turbulence ensures that more of the resulting stars will be born with a greater allotment of fuel, destined for short, brilliant, and explosive lives. The influence of these massive stars, however, does not end with their formation. They immediately begin to reshape their own nurseries with tremendous force, unleashing a feedback loop that can both create and destroy. These stellar titans, born from the chaos of a galactic collision, are not gentle giants. From the moment they ignite, they unleash a ferocious wind of radiation and charged particles, a hurricane of energy that carves into the very gas clouds that gave them life. This is the beginning of stellar feedback, a cosmic dialogue where creation and destruction become two sides of the same coin. The most massive of these stars live fast and die young, concluding their brief lives in supernova explosions of unimaginable power. These blasts do more than just light up the cosmos. They are the primary forges of the universe's heavy elements. Within their incredible heat and pressure, atoms are fused together into elements like carbon, oxygen, and iron, the very building blocks of planets and life. As the astrophysicist Subrahmanyan Chandrasekhar once reflected, "The stars are not wanted now, put out everyone." His words capture the essence of this feedback, where supernova effectively terminate the era of star birth by blasting away the surrounding gas, dispersing the raw material for future stars. This explosive dispersal seeds the galaxy with these newly forged metals, enriching the interstellar medium for eons to come. But how does this violent process actually play out on a galactic scale? Look at the Tarantula Nebula, a vast stellar nursery in our neighboring Large Magellanic Cloud. Here, the combined stellar winds and radiation pressure from a central cluster of supermassive stars have blown a gigantic cavity in the surrounding gas. At the edges of this expanding bubble, the shockwave has compressed the gas, triggering the birth of a new generation of stars. Yet deep inside the cavity, the gas has been completely evacuated, leaving a void where no new stars can form. This is the central paradox of feedback. It is both a trigger and a suppressant. The outcome depends entirely on the environment. In a dense, tightly packed cloud, a supernova's energy might be absorbed, leading to more compression and further star formation. But in a more diffuse region, that same explosion can simply blow the gas away, shutting down star birth entirely. This creates a self-regulating galactic ecosystem. A ferocious starburst cannot last forever because it sows the seeds of its own demise by creating the massive stars whose violent deaths will ultimately quench the fire. This delicate balance between creation and destruction forces us to look beyond the initial firestorm to the lasting legacy left behind when the brilliant chaos finally subsides. What kind of galaxy emerges from the ashes of such a transformative event? Amidst the fading brilliance of a galactic starburst, a more permanent legacy is born. Dazzling clusters of stars, thousands or even millions strong, shine as enduring beacons of that ancient collision. These are not random collections, but families of stars born together from the same compressed cloud of gas, all gravitationally bound in a tight embrace. They serve as cosmic fossils, preserving the story of the merger long after the galaxies involved have settled into a new, quiet form. The process begins within the most violently compressed pockets of gas. When a giant molecular cloud is shocked and squeezed by the forces of a collision, it does not just form individual stars. It can undergo a coordinated collapse, fragmenting into a dense swarm of protostellar cores all at once. Because these newborn stars are born so close together, their mutual gravity is strong enough to tie them into a single, stable unit, a star cluster that can survive for billions of years. There are two primary types of these clusters, each telling a different part of the story. Open clusters are younger, containing hundreds or thousands of stars in a relatively loose grouping. They are often found within the spiral arms of galaxies and are the direct, fresh products of ongoing star formation, including that spurred by collisions. But they are not built to last, their looser gravitational bonds eventually being broken by interactions with other clouds and stars. The true long-term survivors are the globular clusters. These are ancient, dense spheres containing hundreds of thousands to millions of stars, all crammed into a region just a few dozen light years across. Their incredible density gives them immense gravitational binding energy, allowing them to withstand the tidal forces of their host galaxy for eons. For a long time, astronomers believed globular clusters were exclusively relics from the initial formation of the galaxy itself. But research now suggests something profound. Some globular clusters may form exclusively in the violent conditions of galaxy mergers. This means that the population of globular clusters orbiting a galaxy is like a layered archaeological record. Our own Milky Way provides a perfect example. The ancient globular clusters swarming in our galaxy's halo are not all the same age. Some are truly primordial, but others bear the chemical signatures and ages that link them to past events. Many are now thought to be the cores of ancient dwarf galaxies that were torn apart and absorbed by the Milky Way billions of years ago. Their star clusters, however, were so tightly bound that they survived the destruction of their parent galaxy intact and now orbit our own as celestial trophies of these long-concluded cosmic battles. How do astronomers actually read this ancient record? They study the specific chemical composition of the stars within a cluster. Stars born from the same gas cloud will share a distinct metallicity, a specific fingerprint of heavy elements. By measuring this, we can trace clusters back to a common origin, grouping them into families that tell the story of different merger events throughout deep time. These glittering swarms are more than just beautiful, they are permanent signatures written in starlight, a direct and enduring link to the universe's most transformative collisions. The light from a galactic collision is a messenger from a distant past, carrying encrypted stories of stellar birth and destruction. To decode these messages, astronomers act as cosmic detectives, employing a suite of advanced telescopes that see far beyond the narrow rainbow of visible light. Each wavelength of light, from radio waves to gamma rays, reveals a different chapter of the story. Edwin Hubble once noted that the history of astronomy is a history of receding horizons, and today's instruments, like the James Webb Space Telescope, are pushing those horizons back to the very dawn of time. When we look at a merging galaxy in optical light, we see the brilliant blue glow of massive young stars, the immediate result of the collision star-forming fury. But this visible light tells an incomplete story, as it cannot penetrate the thick, opaque clouds of dust that shroud the most active stellar nurseries. This is where infrared astronomy becomes our most powerful tool. Dust, heated by the embedded newborn stars, glows brightly in infrared wavelengths. The James Webb Space Telescope, with its unprecedented infrared sensitivity, acts like a cosmic thermal camera, peering straight through the dust to reveal the hidden cradles of star formation within colliding giants like the Antennae galaxies. To understand the full picture, we must also find the raw material, the cold molecular gas that hasn't yet collapsed into stars. This is the domain of radio astronomy. Massive dishes like the Atacama Large Millimeter Array, ALMA, tune into the faint radio whispers emitted by molecules like carbon monoxide. These observations map the distribution and motion of the invisible fuel, showing us how the collision has funneled and compressed vast reservoirs of gas, setting the stage for the next generation of stars. How do we translate this light into a star formation rate? The key lies in spectroscopy, the practice of splitting light into its constituent colors. Specific elements in the heated gas around young stars emit light at very precise wavelengths, creating bright emission lines. The strength of a hydrogen alpha line, for instance, serves as a direct gauge of how many massive stars are pouring out ultraviolet radiation, allowing astronomers to calculate the incredible pace of star birth in a starburst. Yet, these observations are just single frames in a billion-year-long movie. This is where theoretical models and computer simulations become essential. Astronomers input the laws of physics into powerful supercomputers to simulate galactic collisions. testing different angles and speeds to see which virtual merger best reproduces the intricate shapes and star formation patterns we observe in real galaxies. The legendary Hubble Deep Field images provide a critical piece of this puzzle. They are not just beautiful pictures, they are core samples of the universe, capturing thousands of galaxies at different distances and therefore different epochs. This allows scientists to assemble a flipbook of galactic evolution, observing mergers at various stages to piece together the entire life cycle. Interpreting this cosmic data is fraught with challenges. Dust doesn't just hide things, it can also redden and dim starlight, misleading our measurements. A more subtle problem is projection effects, where two galaxies that appear to be colliding from our vantage point might actually be far apart in the vast depths of space, one merely lying in front of the other. It is only by combining multi-wavelength observations with sophisticated simulations that we can confidently distinguish a true cosmic collision from a simple trick of perspective, slowly unraveling the true narrative of how chaos gives birth to light. The silent, patient work of deep time finds its voice inside the hum of a supercomputer. Here, in lines of code and vast digital universes, astronomers compress billions of years into mere seconds, rendering the majestic collision of galaxies to witness the birth of stars. These numerical simulations are our virtual laboratories, allowing us to experiment with cosmic forces on scales we could never recreate. The Illustris project, one of the most ambitious of these virtual universes, has demonstrated a crucial duality. Simulations show that mergers can drive both star formation and quenching. They are the key to understanding how the same event that ignites a brilliant firestorm of new suns can also, eventually, lead to that fire going out. The foundation of these models rests on two powerful types of code working in concert. N-body simulations track the gravitational dance of billions of individual star particles, calculating their intricate pulls and shoves as galaxies intertwine. But gravity alone cannot tell the whole story. Hydrodynamical codes add the vital layer of gas dynamics, modeling how those vast reservoirs of interstellar gas are compressed, shocked, and heated by the collision. This digital gas can even form virtual stars, which then unleash their own feedback, the powerful radiation and supernova explosions that blow material away. Every simulation begins with a set of initial conditions, a digital snapshot of two galaxies based on our observations of real systems like the Milky Way and Andromeda. Scientists then set the cosmic clock running, watching as the virtual galaxies spiral toward each other. The true test of these models comes from comparing their final outputs with the real universe. Do they produce the same distorted shapes, the same star formation rates, the same telltale chemical signatures we observe in actual colliding galaxies? When the simulation matches reality, we know our underlying physics is likely correct. We can even fast forward into our own galactic future. Simulations of the impending merger between the Milky Way and Andromeda paint a vivid picture. They predict that in about 4 billion years, the gravitational turmoil will trigger a significant burst of star formation, a final blaze of stellar birth before the two galaxies settle into a single, quiet elliptical giant. Yet these virtual universes are only as good as the physics we program into them. Their accuracy constantly improves as we incorporate better understandings of magnetic fields, dark matter behavior, and the complex nuances of stellar feedback. How do we know these digital prophecies hold any truth? We test them against the most spectacular cosmic wreckage we can find, turning our telescopes to specific case studies where the theory of deep time meets the evidence written in starlight. Two spiral galaxies are caught in a final, intimate dance, their classic shapes already torn asunder. Known collectively as the Antennae galaxies, this pair offers us a front-row seat to a cosmic transformation happening just 60 million light-years away. Their long, streaming tails, drawn out by gravitational tides, are not made of stars alone, but are also vast rivers of gas and dust, the primordial ingredients for what comes next. Within this chaotic wreckage, the universe is conducting a grand experiment in star formation. Astronomers have identified over 1,000 young, brilliant star clusters scattered across the system, each one a family of thousands to millions of stars born from the same compressed cloud of gas. This makes the Antennae a living laboratory, a snapshot of a starburst in furious progress. The timeline of this collision is written in their distorted shapes. The two spirals first began their gravitational tango a few 100 million years ago, a mere moment in cosmic terms. As they swung past each other, their mutual gravity acted like a cosmic fist, violently compressing the immense molecular clouds drifting within them. This sudden, extreme pressure pushed the gas past a critical threshold, triggering a chain reaction of collapse and ignition. We see the evidence not just in visible light, but in the heat radiating from the dust itself. Thick clouds of dust, warmed by the embedded baby stars, glow intensely in infrared light. These regions are the hidden stellar nurseries, invisible to optical telescopes, but blazingly clear to infrared eyes like those on the James Webb Space Telescope. Some of the youngest and most massive clusters here are known as superstar clusters, so dense and bright they outshine entire small galaxies. What does the future hold for this spectacular pair? Their dance is far from over. They are destined to swing past each other again, eventually merging completely into a single, massive elliptical galaxy, a quiet giant where the fire of star birth has long since faded. How does this nearby chaos compare to the most extreme collisions happening across the universe, where the forces at play are almost beyond comprehension? ARP 220 outshines our entire Milky Way by more than 50 times, yet it does so in a light our eyes cannot see. This colossal beacon is an ultra-luminous infrared galaxy, a class of cosmic objects where the true fury of creation is hidden behind a thick, opaque veil of dust. It represents the final, spectacular product of a galactic merger now nearing completion. At its heart lie not one, but two distinct galactic nuclei, the dense surviving cores of the two spirals that collided, now orbiting each other in a tight, frantic embrace only about 1,000 light-years apart. The entire system is a maelstrom of raw material and relentless energy. Astronomers measure its star formation rate at a staggering 100 solar masses per year. This means every 12 months, enough gas and dust collapses to form 100 new stars the mass of our Sun. Compare that to the Milky Way, which manages just 1 or 2 solar masses per year, and you begin to grasp the sheer scale of the firestorm raging inside ARP 220. Where does all this fuel come from? The galactic collision funneled an almost unimaginable amount of gas into the central region. Observations from radio telescopes like ULMA have mapped these reserves, revealing massive, turbulent reservoirs of molecular gas. This gas is not sitting idle. It is being compressed into incredibly dense knots and filaments, creating conditions ripe for the birth of not just individual stars, but of entire superstar clusters. These clusters are so packed together and so brilliant that their combined radiation heats the surrounding dust to immense temperatures, causing it to glow with the intense infrared light that defines this class of galaxy. This incredible burst of creation, however, carries the seeds of its own destruction. Such a ferocious rate of star formation cannot be sustained. The system is rapidly depleting its vast gas reserves, living through a brilliant but brief binge that will inevitably lead to a cosmic hangover. As the most massive of these new stars explode as supernova, they will blast away the remaining gas, effectively quenching further star formation and leaving behind a more quiescent, aging galaxy. But there is another, even more extreme potential outcome for such a violent merger. The immense concentration of mass and gas at the very center of ARP 220 can do more than just make stars. It can also feed a supermassive black hole. What happens when the energy of an entire galaxy's worth of material is funneled not into starlight, but into a single, terrifying point of no return? This unseen architecture, this ghostly scaffold of dark matter, orchestrates the entire cosmic collision from the shadows. While the brilliant fireworks of star birth capture our attention, they are merely a consequence of a far deeper gravitational drama. Vera Rubin's pioneering work revealed that galaxies rotate so swiftly they should tear themselves apart, held together only by the immense, invisible grip of dark matter. This same principle governs their most violent interactions. Each galaxy we see is embedded within a vast, diffuse halo of this mysterious substance, a halo that extends far beyond the luminous stars and gas. When two galaxies approach one another, it is these colossal dark matter halos that first make contact, their gravitational fields intertwining long before the stars themselves ever meet. This initial handshake between invisible giants sets the rules for the entire encounter. The shape and density of these dark matter halos determine the orbital path the galaxies will take. A slow, grazing pass allows for dramatic tidal forces to stretch the galaxies into long streams, while a more direct, head-on collision funnels gas violently toward the center. The now famous Bullet cluster offers stunning proof of this dynamic. Observations show that during a high-speed collision between two galaxy clusters, the clouds of hot, colliding gas were slowed and separated from the bulk of the mass, which was mapped through gravitational lensing. That mass, the true source of gravity, was found to be offset, proving it was carried by the dark matter halos that passed through one another virtually unaffected. This invisible framework dictates the merger's rhythm and ultimate outcome. Simulations show that a galaxy with a more extended dark matter halo will experience a slower, more drawn-out merger, while a compact, dense halo can lead to a rapid and violent coalescence. This timescale is everything. A slower merger provides more time for gravitational tides to stir and compress the galactic gas, potentially leading to more widespread and prolonged episodes of star formation. So how does this invisible hand indirectly foster the birth of stars? Dark matter creates the deep gravitational wells, the cosmic valleys, that guide the flow of everything else. It sculpts the overall potential energy landscape of the collision. As the visible galaxies pass through each other, the surrounding dark matter halos exert a continuous pull, dragging the interstellar gas along specific pathways. This guided flow is what channels vast reservoirs of cold gas into the central regions, piling it up and creating the extreme densities necessary to ignite a starburst. The dark matter does not form stars itself, but it builds the stadium and writes the playbook for the game. It is the ultimate cosmic stage manager, unseen but undeniably in control, setting the conditions under which the brilliant chaos of creation can unfold. This gravitational guidance system ensures that the collision's energy is focused, transforming a random crash into a structured, transformative event that reshapes the very heart of a galaxy. Deep within the heart of a galactic collision, a sleeping giant awakens. As titanic forces funnel vast rivers of gas toward the galactic core, they do more than just ignite starbursts, they feed a supermassive black hole. This is the birth of an active galactic nucleus, or AN, a cosmic engine of unbelievable power. The same tidal forces that compress gas clouds to form stars also relentlessly drive material inward toward this ultimate point of no return. As gas spirals into the black hole's accretion disk, it heats to millions of degrees, blazing with radiation that can outshine every star in the galaxy combined. This is not a gentle process, it is a violent feast, and the aftermath can reshape the entire galaxy. We see this dramatic duality in systems like NGC 6240, a galaxy still reeling from a merger. Within its chaotic core, astronomers have spotted not one, but two brilliant active nuclei, the supermassive black holes from the original galaxies, now both gorging on the gas delivered by their collision and orbiting each other in a tight, deadly dance. This simultaneous ignition shows how efficiently a merger can trigger black hole activity. But what happens after the feast begins? The AGN does not consume quietly. It unleashes powerful jets and winds, torrents of energy that scream outward from the poles of the black hole. This is AGN feedback, a regulatory force that can both create and destroy. In some cases, these outflows can compress surrounding gas clouds, giving star formation an extra nudge. But in others, they act as a cosmic fire extinguisher. When the AGN outburst is particularly violent, its immense energy can heat the galactic gas to such extreme temperatures that it can no longer collapse to form new stars. Even more dramatically, these winds can blast the remaining gas reservoir clean out of the galaxy, stripping it of the raw material for future generations of suns. This creates a fundamental balance between creation and suppression. The merger provides the fuel for both a starburst and a hungry black hole. The black hole then feasts, and its resulting outburst can ultimately quench the very starburst that gave it life. This self-limiting cycle helps explain why the most intense periods of star formation are so brief. The galaxy is essentially cutting off its own fuel supply in a spectacular display of cosmic regulation. The brilliant, chaotic firestorm of creation gives way to a more settled but sterile future. The brilliant chaos finally subsides, leaving behind a fundamentally transformed galaxy. This is the quiet aftermath of a cosmic collision, a state astronomers call a merger remnant. The ferocious starburst has burned out, having consumed or expelled its vast reserves of gas. What remains is a new celestial entity, often a smooth, featureless elliptical galaxy, its once distinct spiral arms erased by the violence of the encounter. The stars themselves have been violently relaxed, a process where gravitational interactions during the merger completely scramble their orderly orbits, redistributing them into a random, swarm-like halo. Without the cold gas needed to form new, blue stars, the galaxy's population steadily ages and reddens, becoming a quiet giant dominated by ancient suns. This final form is not always an elliptical, however. Some mergers, particularly minor ones where a small galaxy is consumed by a larger spiral, can actually rejuvenate the larger disk, funneling fresh gas into its arms and sparking a new, more subdued chapter of star formation. The iconic Sombrero Galaxy, with its brilliant central bulge and distinct dust lane, may very well be the product of such a past satellite merger. So what determines the ultimate fate of these cosmic unions? The final structure hinges on the initial conditions of the collision. The mass ratio of the two galaxies is paramount. A major merger between two equals most often produces an elliptical, its stars thoroughly randomized. The gas content is equally critical. A gas-rich collision fuels a brilliant starburst that rapidly depletes the fuel, while a gas-poor merger between two already aged galaxies results in a quieter consolidation. We can read this history in the motion of the stars. In a spiral galaxy, stars orbit in an orderly, rotating disk. In an elliptical like the colossal M87, stellar motions are random and chaotic, a clear kinematic signature of a violent past. The supermassive black hole at its heart and the vast swarm of globular clusters encircling it are likely trophies from multiple galactic acquisitions throughout deep time. This cycle of collision and rebirth is not a cosmic anomaly. It is a fundamental pattern of growth, a process that builds the largest galaxies and writes their final chapters in the silent, red light of aging stars. The history of the cosmos is written in the shapes of its galaxies. Each majestic spiral and smooth elliptical tells a story of past encounters, of gravitational dances that either preserved a delicate disk or scrambled it into a swarm of stars. This grand narrative is governed by a process known as hierarchical structure formation, a simple but powerful idea where small building blocks merge to create ever larger structures. In the early, denser universe, these galactic collisions were a frequent occurrence, a primary driver of cosmic assembly that forged the first large galaxies from a sea of smaller fragments. This higher merger rate in the past fundamentally shaped the stellar populations we see today. We find evidence of this in distant galaxy clusters. Astronomers Beverly Oemler and Augustus Butcher made a startling discovery. Clusters billions of years ago contained a much higher fraction of blue, star-forming galaxies compared to the red, dead giants that dominate similar clusters now. This Butcher-Oemler effect points to a more active, tumultuous past, where galaxy interactions within clusters were constantly triggering bursts of star formation, painting entire regions of space blue with newborn suns before those fires were eventually quenched. The classic Hubble sequence, that beautiful tuning fork diagram separating spirals from ellipticals, is more than just a classification scheme. It is a snapshot of different evolutionary paths, largely dictated by an individual galaxy's merger history. A quiet, isolated spiral can maintain its elegant structure for eons, but a major collision between two such spirals will almost certainly erase those delicate arms, randomizing stellar orbits to create a smooth, featureless elliptical. Our own Milky Way sits on this sequence, its specific spiral shape a testament to a relatively peaceful recent history, though its halo is littered with the remnants of smaller galaxies it has consumed. These collisions do more than just reshape galaxies, they build them from the ground up. The vast, diffuse halo of stars surrounding large galaxies like our own is not primordial. It is an archaeological dig site, built up over billions of years from the shredded remains of countless smaller satellite galaxies. Each merger, no matter how minor, contributes stars to this halo and adds to its population of ancient, tightly bound globular clusters. This growth is intricately linked to the universe's large-scale structure, the cosmic web of filaments and voids. Galaxies are not scattered randomly. They are strung along these invisible threads of dark matter. It is at the intersections of these cosmic filaments, within the dense knots of galaxy clusters, where mergers are most frequent and most dramatic, driving the evolution of the most massive galaxies in the universe. This cycle of collision and consolidation has profoundly influenced the chemical enrichment of the cosmos. When galaxies merge, they stir their gas reservoirs, mixing pristine hydrogen with heavier elements forged in stellar furnaces and scattered by supernovae. This process seeds the interstellar medium with the complex ingredients necessary for rocky planets and, ultimately, life. The very elements that make up our world were likely mixed and distributed more efficiently by the chaotic churning of galactic collisions throughout cosmic history. The very elements that breathe life into our world were forged in these collisional crucibles. Within the furious starbursts ignited by galactic mergers, the universe conducts its most advanced alchemy, transforming primordial hydrogen and helium into the complex atoms that build everything from rocky planets to living cells. This process, known as nucleosynthesis, is supercharged in these chaotic environments. As Carl Sagan so poetically noted, we are made of star stuff, and here we witness the factory where that stuff is created on an industrial scale. The most massive stars, those born in such great numbers during a starburst, are the primary forgers. They live for only a few million years before dying in spectacular core collapse supernova. In the heart of these titanic explosions, temperatures and pressures reach unimaginable extremes, fusing atoms together to create a suite of elements like oxygen, neon, magnesium, and silicon. These are known as alpha elements, and they are the fundamental bricks for building terrestrial worlds. The violence of the supernova then blasts these newly forged metals out into the surrounding interstellar medium, seeding the galactic gas with this enriched material. This dispersal is amplified by powerful stellar winds that blow from massive stars throughout their short lives, continuously polluting their environment with heavy elements. We can observe the result of this enrichment by studying the metallicity, the abundance of elements heavier than helium within merged galaxies. Often, astronomers find distinct metallicity gradients where the central regions, having experienced the most intense star formation, are far more metal-rich than the outer edges. Furthermore, spectroscopic observations frequently reveal enhanced ratios of alpha elements to iron in starburst regions. This is a telling signature of rapid, coordinated chemical enrichment, because these alpha elements are produced quickly in massive stars and spewed out by their supernova, while iron is produced more gradually over longer timescales. For a local, quieter example of this process, we can look to the Orion Nebula in our own Milky Way. It is a nearby stellar nursery where massive stars are enriching the local gas cloud, a small-scale demonstration of the principles that operate globally in a colliding galaxy. A major merger simply takes this process and amplifies it to a cosmic volume, turning an entire galaxy into a sprawling chemical factory. The legacy of this frantic period of creation and destruction is profound. It fundamentally enriches the galaxy, ensuring that the next generation of stars formed from this recycled material will be born with a higher metallicity. These metal-rich stars are far more likely to form planetary systems with rocky, Earth-like worlds. The iron in our blood, the calcium in our bones, and the oxygen we breathe were all created in such stellar furnaces, scattered by ancient explosions and mixed by the gravitational turmoil of galactic encounters. This chemical evolution, written in the light of every star, directly paves the way for cosmic habitability. It forces us to ask a deeper question about our own place in this cycle. Did our solar system itself owe its specific composition to a long-forgotten galactic encounter that enriched our corner of the Milky Way eons ago? A planetary system emerging within a galactic collision faces a cosmic paradox of creation and destruction. On one hand, the furious starburst forges and scatters the essential elements for rocky, Earth-like worlds. On the other, that same stellar fury bathes any nascent planets in an unrelenting storm of radiation. This is the ultimate question of habitability in a violent universe, a delicate balance where the very forces that build a world can also tear it apart. Intense ultraviolet light from massive, newborn stars can strip away the atmospheres of orbiting planets, while nearby supernova explosions unleash waves of lethal gamma rays and cosmic rays capable of sterilizing entire systems. The shock waves from these blasts could even disrupt the fragile protoplanetary disks where infant planets are still assembling. Yet, this chaos is also a cosmic delivery service. The same supernova that threaten life are the primary source of heavy elements like iron, silicon, and oxygen, the raw materials for terrestrial planets. They enrich the interstellar medium, ensuring that the next generation of stars forms from gas already rich in the building blocks of complexity. our own solar system may be a product of such an ancient triggered event. The specific isotopic ratios found in meteorites suggest that a nearby supernova explosion may have injected material into our primordial solar nebula, potentially even triggering the collapse that led to the Sun's birth. This implies our planetary home and we ourselves could be a direct legacy of a stellar cataclysm that occurred billions of years ago. So, do collisions make galaxies more or less habitable? The answer is a profound and complex yes to both. In the short term, the core of a merging galaxy becomes a death zone, a region of such extreme radiation that life as we know it would struggle to originate or survive. But in the long term, across billions of years, these events enrich the entire galactic reservoir. They seed the spiral arms and quiet suburbs with the recycled, metal-rich gas that makes rocky planet formation not just possible but probable. The galaxy is effectively trading localized, immediate habitability for a wider, more enduring potential for life later on. This cosmic cycle of death and rebirth forces us to look forward, to predict where the next great collisions will occur and how they might reshape the habitability of entire galactic neighborhoods in the eons to come. Our own galaxy is not an island in eternity, but a traveler on a long-term collision course. The Andromeda Galaxy, a faint smudge in our current night sky, is hurtling toward the Milky Way at a speed of over 250,000 miles per hour. This is not a possibility, but an inevitability, a future written in the precise measurements of the Hubble Space Telescope. Based on that data, we know the initial impact will occur in about 4.5 billion years. As Andromeda approaches, it will transform from a hazy patch into a brilliant, sprawling tapestry of light, eventually dominating the heavens. What would a being on Earth witness across this immense timescale? The first close pass will be a slow-motion cataclysm. Gravity will warp both galaxies into spectacular, distorted shapes, stretching them into long, luminous streams of stars. Yet, amidst this cosmic violence, a remarkable calm will persist for individual solar systems. The spaces between stars are so vast that direct stellar collisions are incredibly unlikely. The real drama will unfold in the interstellar gas. Immense clouds of hydrogen will be violently compressed, slamming into one another and igniting a firestorm of new star formation. The night sky would begin to blaze with the light of millions of newborn suns, a celestial fireworks display lasting for millions of years. This brilliant starburst phase will be followed by a long gravitational dance. The two galaxies, having swung past each other, will fall back together, their cores orbiting one another in an ever-tightening spiral. Over another 1 to 2 billion years, they will complete their final merger, coalescing into a single, new galaxy that astronomers have nicknamed Milky Way. In this final act, our solar system will likely be flung far out into the galactic halo, pushed to the remote outskirts of the new elliptical giant. The familiar band of the Milky Way would be gone forever, replaced by a vast, spherical swarm of older, redder stars. This predicted future forces a profound reflection on our place in the cosmos. How do we, with our fleeting lifetimes, confidently forecast events billions of years hence? The answer lies in the universal language of physics. By measuring the motion and mass of Andromeda and applying the same laws of gravity that govern a falling apple, we can extrapolate the cosmic dance forward in time. Our certainty comes not from guessing, but from calculating the unyielding trajectory set by mutual gravitational attraction. This grand prediction offers a humbling perspective, connecting our present moment to the ultimate fate of our galactic home. Our view of these cosmic collisions is about to be transformed by a new generation of eyes on the sky. The James Webb Space Telescope is already revolutionizing our perspective, peering through the thick dust of merging galaxies to reveal the fiery cradles of star birth within. Its early image of the Cartwheel Galaxy is a perfect example, showing intricate structures of young stellar clusters and the reverberating shock waves from the collision in stunning, unprecedented clarity. This is just the beginning of a new observational era. Soon, the Nancy Grace Roman Space Telescope will join the effort, conducting vast wide-field surveys that will find thousands of interacting galaxies across cosmic time. On the ground, the colossal mirrors of the extremely large telescopes will act as cosmic microscopes, resolving fine details within galactic cores and directly imaging the regions around supermassive black holes. These instruments are not just bigger, they are smarter, equipped with advanced technologies like integral field spectroscopy. This powerful technique doesn't just take a picture, it captures a three-dimensional data cube, allowing astronomers to map the violent motions of gas as it swirls and compresses during a merger. This reveals the invisible forces at work, showing us the physics of star formation in action. Even the public is becoming part of this discovery process through citizen science projects, where volunteers help classify the strange and wonderful shapes of colliding galaxies in vast digital sky surveys. The ultimate goal of these technological marvels is to push our vision back to the dawn of structure in the universe. What mysteries do they hope to solve? They are searching for the very first galaxies to ever merge, the initial seeds of hierarchical growth that began the long process of building the cosmic giants we see today. How far back can we trace this cycle of collision and creation? And what did the first stellar firestorms look like in the pristine early universe? The first galaxies ignited in a universe still cloaked in primordial darkness, their light piercing the cosmic dawn. These initial stellar islands were not isolated. They were already colliding, merging, and cannibalizing one another in a frantic dance of assembly. The early cosmos was a far denser and more chaotic place, a crucible where gravity worked with brutal efficiency to build structure from the raw material of the Big Bang. Within this crowded, turbulent environment, galactic encounters were not rare events. They were a fundamental part of growth. The James Webb Space Telescope has shattered our expectations by revealing surprisingly massive galaxies at incredibly high redshifts, meaning we are seeing them as they existed only a few 100 million years after the universe began. Their existence so early defies simpler models of slow, steady growth, pointing directly to a violent youth dominated by rapid, efficient mergers. These ancient collisions operated under a different set of physical laws. The protogalaxies were brimming with pristine gas, cool and dense, offering a nearly unlimited fuel supply for star formation. There were no heavy elements yet to help the gas cool efficiently, yet the sheer abundance of hydrogen and the incredible forces of compression during collisions overcame this. The environment was one of extreme turbulence, with gas flows and shock waves ripping through the young structures, creating ideal conditions for the birth of massive stars. We see evidence of this frantic assembly in objects known as Lyman break galaxies. These are systems so distant that their light has been stretched or redshifted to a point where a key feature, the Lyman break, is shifted into observable wavelength. Many of these distant, brilliant smudges show distorted, clumpy morphologies, classic signatures of ongoing mergers captured by the deep gaze of telescopes like Hubble and now Webb. Take the galaxy GNZ 11, observed at a redshift of 11, meaning we see it as it was over 13.3 billion years ago. It is impossibly bright and massive for its time, a beacon whose existence is best explained by a history of rapid mergers, a series of violent unions that funneled gas inward and sparked a ferocious starburst. This early frenzy of creation did more than just build galaxies. It transformed the universe itself. the intense ultraviolet radiation pouring out from the countless massive stars born in these mergers began to rip electrons from the atoms of the neutral hydrogen gas that filled all of space. This epoch, known as cosmic reionization, was a pivotal transition where the cosmos became transparent to light, and it was likely driven by the collective fury of starbursts from countless merging galaxies. Observing these specific events, however, pushes our technology to its absolute limits. The signals from such vast distances are incredibly faint, and the details of the merging systems are often blurred into a single pixel of light, requiring sophisticated computer models to interpret. Yet, by piecing together this evidence, we understand that the vast cosmic web we see today, with its elegant filaments and majestic galaxy clusters, was woven together by the gravitational pull of dark matter and stitched into light by the brilliant, explosive threads of these earliest collisions. The foundations of our modern universe, including the giant elliptical galaxies at the hearts of clusters, were forged in the relentless mergers of the cosmic dawn. This cosmic web of dark matter dictates the flow of galaxies and the rhythm of their collisions. Picture the universe not as a random scattering of stars, but as an immense, intricate network of gravitational threads. Galaxies are strung along these invisible filaments like luminous beads, slowly sliding toward the dense intersections where clusters form. It is at these crowded cosmic crossroads, these nodes in the web, where the dance of galaxies becomes most frantic and mergers are a common destiny. The environment a galaxy inhabits directly controls its fate. In the sparse, lonely voids between filaments, galaxies can spin in isolation for billions of years, their spiral arms remaining pristine. But within the dense, bustling neighborhoods of galaxy clusters and groups, close encounters and violent unions are frequent. The Virgo cluster, our nearest massive gathering of galaxies, is a perfect example. Here, astronomers observe numerous galaxies with distorted shapes and long tidal tails, clear evidence of past and ongoing gravitational interactions. Why are these clusters such fertile ground for collisions? The immense collective gravity of the cluster creates powerful tidal fields, a stretching force that can pull galaxies out of their comfortable orbits and send them on collision courses with their neighbors. This process, known as galaxy harassment, is a slow but relentless driver of mergers in these crowded environments. The dark matter halos surrounding each galaxy are the true architects of this large-scale structure. They form the underlying skeleton of the cosmic web, their gravitational pull guiding the flow of gas and the motion of galaxies along the filaments. When two dark matter halos intersect during a cluster merger, they dictate the dynamics of the entire event, funneling the visible galaxies within them toward their fate. This rate of cosmic collision is not constant. It has changed dramatically over the universe's lifetime. In the early, denser cosmos, galaxies were packed closer together and merger rates were far higher. This was the era of rapid assembly, when the first giant galaxies were built from a sea of smaller fragments. But as the universe has expanded, galaxies have been carried farther apart. The average distance between them has increased, making close encounters and major mergers less frequent in the recent universe. This decline in interaction rates is a fundamental part of cosmic evolution. It helps explain why the most intense starbursts, those brilliant firestorms of star birth, were more common in the distant past. The universe has, in a sense, settled down. The frantic construction phase is largely over, leaving behind the majestic but quieter galactic giants we see today. This evolving cosmic structure raises a profound question about our own galactic home. How has the Milky Way's specific location within this vast web influenced its own peaceful history and its inevitable future collision? The brilliant clarity of our cosmic simulations often fades at the edge of observation, where the messy details of reality introduce profound mysteries. Even with our advanced understanding, fundamental questions about colliding galaxies remain stubbornly open. The celebrated physicist Richard Feynman once expressed a preference for questions that cannot be answered over answers that cannot be questioned, and in this spirit, we must confront the limits of our knowledge. One of the most puzzling enigmas is why two seemingly identical galactic collisions can have wildly different outcomes. Why does one merger ignite a firestorm of star birth, while another, with similar masses and trajectories, results in a relatively quiet union? The initial conditions appear the same, yet the stellar output is not. Large-scale surveys like the SOMI project are now mapping thousands of galaxies to untangle this riddle, looking for subtle differences in gas density, pre-existing structure, or the dynamics of the dark matter halos that might explain the divergence. Another great unknown is the influence of magnetic fields. These invisible lines of force are woven through the interstellar medium, and during a collision, they can be amplified and stretched to incredible intensities. Do these magnetic fields act as a cosmic scaffolding, helping gas clouds resist collapse, or do they channel and focus the flows, making star formation even more efficient? We simply do not yet know. Then there is the puzzle of efficiency. We see vast reservoirs of cold molecular gas in merging galaxies, but only a fraction of it ever turns into stars. What determines this final efficiency? The answer may lie in the different phases of the interstellar medium, the complex interplay between cold, dense clouds and the hot, surrounding plasma that our current telescopes struggle to resolve. Even minor mergers present a conundrum. These events, where a small dwarf galaxy is consumed by a giant spiral, are far more common than major collisions. While they lack the spectacular drama of the Antennae galaxies, could these gentle acquisitions be the steady, background trickle that constantly rejuvenates spiral disks and sustains low-level star formation over cosmic time? Solving these mysteries requires more than just bigger telescopes. It demands a new way of seeing. The next great leap may come from multi-messenger astronomy, which combines light with other cosmic signals, like the ripples in spacetime known as gravitational waves. While these waves are currently used to study merging black holes and neutron stars, future observatories could potentially sense the background hum of entire populations of these objects, a fossil record of the intense star formation and stellar death that occurs during galactic collisions. What hidden chapters of the collision story are written in this invisible language? Ripples in the fabric of spacetime itself offer a whisper of confirmation for our grandest cosmic theories. When massive objects like black holes or neutron stars spiral into each other, they do not just flash with light, they shake the universe, sending out gravitational waves that stretch and compress everything in their path. Our most sensitive detectors on Earth, like LIGO and Virgo, have begun to catch these faint tremors, opening a window into the final moments of stellar remnants born from the very stellar firestorms we have been discussing. Each chirp of a gravitational wave signal tells a story of a violent end that began with a violent birth. The connection is profound. Galaxy mergers create the perfect conditions for forging the massive stars that swiftly evolve into the black holes and neutron stars that eventually merge. So, while LIGO and Virgo detect the final act, they are indirectly probing the star-forming frenzy of ancient galactic collisions. But the future holds an even more direct view. A space-based observatory called LISA is being designed to listen for the low-frequency hum of supermassive black hole binaries, the colossal engines at the hearts of merging galaxies. These pairs, brought together by the galactic dance, spiral inward over eons, and their eventual collision will ring spacetime like a bell, Detecting that chorus would provide an unambiguous census of galaxy mergers across the cosmos, a history written not in light but in the warping of space itself. This new messenger does not replace traditional astronomy, it completes it. Remember the event known as JW170817, the first merger of two neutron stars seen in both gravitational waves and light. That single event was a Rosetta Stone for cosmic collisions. The gravitational waves gave us the mass and dynamics of the system, while the follow-up observations across the electromagnetic spectrum revealed a kilonova, an explosion that forged and scattered heavy elements like gold and platinum across space. This directly showed how the debris from collisions on both stellar and galactic scales seeds the universe with the building blocks of planets and life. How exactly do these invisible ripples enhance our understanding? They provide pure dynamical information, free from the obscuring effects of dust or gas. They tell us the masses, spins, and distances of the merging objects with unparalleled precision, allowing us to test our models of how these systems form and evolve in the turbulent aftermath of galactic encounters. This convergence of gravitational wave physics and traditional astronomy marks a new, interdisciplinary era where we no longer just watch the cosmos, but we listen to its deepest vibrations. The violent beauty of colliding galaxies draws its narrative not from astronomy alone, but from a chorus of scientific disciplines. Physics provides the fundamental laws, from the gravitational equations that choreograph the dance to the nuclear processes that ignite within stellar cores. To understand the alchemy inside a supernova, we must turn to nuclear physics, which details how immense pressure and heat forge heavy elements from simpler ones. This knowledge lets us decode the light from distant starbursts, reading the specific signatures of oxygen, carbon, and iron that tell us what kind of stellar factories are at work. Chemistry, too, plays a vital role in the earlier stages. The vast, dark molecular clouds where stars are born are complex chemical soups. By studying the spectral lines of molecules like carbon monoxide and even organic compounds, chemists help astronomers understand the initial conditions and cooling processes that allow these cosmic nurseries to collapse. How do we possibly track these multifaceted interactions? We rely on the power of computer science, the breathtaking simulations that model billions of years of galactic evolution are feats of digital engineering, requiring sophisticated algorithms and immense computational power to solve the complex equations of gravity, hydrodynamics, and radiation. This digital universe becomes a testing ground for our physical theories. The interstellar medium itself is a state of matter studied in plasma physics, a seething, magnetized gas whose behavior influences how shockwaves propagate and how energy is transferred. Even biology finds a connection in this cosmic story, tracing the origins of life's essential elements back to those stellar forges and the galactic collisions that distributed them. To communicate these profound, interconnected ideas, we often turn to art. Illustrators and data visualizers transform abstract data and mathematical models into stunning imagery and immersive experiences, making the invisible forces of dark matter and the violent birth of stars accessible to our human senses. This beautiful integration of different fields of knowledge does more than just satisfy curiosity. It prepares us to apply these cosmic lessons in practical ways, pushing the boundaries of technology and our understanding of the universe. These cosmic stories, born from data and simulation, find their most powerful voice when shared with everyone. Planetarium domes transform into portals, immersing audiences in the violent beauty of galactic collisions, while online videos translate billions of years of cosmic evolution into narratives that captivate millions. This vital work of public engagement turns abstract science into a shared human experience. Central to this effort are initiatives like NAS, a universe of learning, which translates the raw data from telescopes like Hubble and Webb into interactive tools and educational materials. These resources allow students and the curious public to explore the same cosmic phenomena that professional astronomers study, bridging the gap between frontier research and public understanding. One of the most direct ways the public contributes is through citizen science. Projects like Galaxies Zoo have enlisted millions of volunteers to help classify the strange and wonderful shapes of galaxies spotted in sky surveys. This collective human effort is not just busy work, it has led to genuine discoveries, including the identification of rare and distorted galaxy systems that might otherwise have been missed by automated algorithms. The visual power of this science is undeniable. The Hubble Heritage Project, for instance, consciously processes and releases astronomical images for their aesthetic value as well as their scientific merit. These stunning vistas of colliding galaxies, with their brilliant blue star clusters and sweeping tidal tails, do more than inform. They inspire a sense of wonder that can ignite a lifelong passion for exploration. This outreach extends to social media, where scientists and institutions demystify their work, and to hands-on activities that make the physics tangible. Simple demonstrations with springs or interactive simulations can model how gravitational tides stretch galaxies, making an invisible force feel real. Amateur astronomers play a crucial role in this ecosystem, their dedicated observations sometimes spotting the subtle signs of a new galactic interaction, proving that discovery is not confined to professional observatories. Why is this broad engagement so essential? It cultivates a society that values and supports fundamental scientific research, ensuring continued funding for the telescopes and missions that push our knowledge forward. It also opens the doors of science wider, encouraging participation from diverse backgrounds and fresh perspectives that will ultimately lead to new questions and new ways of seeing the cosmos. This collective effort to share the story ensures that the next generation of scientists, engineers, and dreamers will be ready to pursue the mysteries that still lie ahead. A decade from now, our maps of galactic collisions will not be flat images, but dynamic three-dimensional models pulsing with the flow of gas and the flicker of newborn stars. The next generation of observatories is poised to transform our static snapshots into a living, breathing movie of cosmic evolution, redefining the very physics we use to describe star birth. One of the most profound shifts will come from the Square Kilometre Array, or SCAR, a revolutionary radio telescope network. Its unprecedented sensitivity will allow it to map the cold, dark molecular hydrogen, the primary fuel for stars, throughout entire merging galaxies. We will no longer just see the aftermath of compression. We will watch in real time as gravitational tides funnel vast rivers of gas into dense knots, predicting where stellar nurseries will ignite before they even light up. This three-dimensional cartography of chaos will be paired with a deep dive into the exotic chemistry of these events. Astronomers are eager to study starbursts in low metallicity environments, similar to the early universe. In these systems where heavy elements are scarce, gas cannot cool as efficiently, potentially leading to the formation of even more massive primordial-style stars that live fast, die young, and enrich their surroundings in unique ways. Another hidden ingredient coming into focus is the role of cosmic rays. These high-energy particles, accelerated by supernova shocks and turbulent magnetic fields, can heat the interstellar medium and influence the pressure within gas clouds. The next decade will seek to answer whether cosmic rays act as a subtle regulator, helping or hindering the final collapse of a cloud into a star. The sheer volume of data from these new missions will be unimaginable, which is why machine learning will become an indispensable partner in discovery. Advanced algorithms will sift through millions of galaxy images to identify rare and fleeting stages of interaction, finding patterns and correlations invisible to the human eye, and running sophisticated simulations to test thousands of collision scenarios overnight. We will also push our vision to the very edge of time, using the James Webb Space Telescope and its successors to directly probe the epoch of reionization. The goal is to catch the first galaxies in the act of merging, to see if their collective starbursts were indeed the primary engines that cleared the cosmic fog and made the universe transparent. This entire forward-looking endeavor is fundamentally interdisciplinary, weaving together data from gravitational wave detectors, neutrino observatories, and telescopes across the electromagnetic spectrum. Each new messenger adds a layer to the story, creating a holistic picture of how gravity, turbulence, and radiation conspire to build a galaxy. The breakthroughs awaiting us will not merely fill in gaps in our knowledge, they will likely force us to rewrite our textbooks on galaxy evolution. This relentless pursuit of understanding, however, carries its own profound weight, inviting us to reflect on the purpose and responsibility that comes with unraveling the universe's deepest secrets. This profound cosmic knowledge carries a weight of responsibility, a quiet challenge to our species. We now understand that our planet, our bodies, and our very existence are products of ancient stellar cataclysms, gifts from a universe that is both creative and destructive. This realization forces us to confront difficult questions about how we choose to use such a perspective. Is it right to invest billions in peering at distant galactic collisions when our own world faces pressing crises of poverty, conflict, and environmental decay? This is not a simple either-or proposition. The same fundamental physics that guides our telescopes also underpins the technologies that monitor our changing climate and connect our global society. The pursuit of cosmic understanding often spins off innovations in computing, medicine, and materials science, yielding practical benefits that ripple through our economies. More importantly, it provides a vital context for our earthly struggles. Learning that the iron in our blood was forged in a long-dead star and scattered by a galactic collision can fundamentally reshape our relationship with this planet. It frames Earth not as a disposable resource, but as an irreplaceable, fragile ark carrying the legacy of that cosmic inheritance. This perspective can inspire a deeper form of environmental stewardship, a recognition that we are custodians of rare and ancient stardust. This cosmic viewpoint also holds the potential to dissolve artificial boundaries. When we see our world as a pale blue dot set against the vast backdrop of an evolving cosmos, nationalistic and ethnic divisions can seem petty and transient. The knowledge that we share a common cosmic origin story could, in theory, become a powerful force for global unity, fostering a sense of shared human destiny. Yet for this to be realized, the science itself must be inclusive. The story of the universe belongs to all of humanity, not just to a privileged few. Ensuring that people from all backgrounds and nations have access to this knowledge and can contribute to its expansion is an ethical imperative. It prevents a new form of cosmic inequality and enriches our collective understanding with a diversity of thought and interpretation. Ultimately, the great lesson drawn from studying deep time and galactic evolution is one of profound humility. It teaches us long-term thinking, forcing us to consider the consequences of our actions across generations, not just election cycles. The universe operates on timescales of billions of years, and our brief moment of consciousness comes with the duty to use our knowledge wisely. We are the universe becomes self-aware, and with that awareness comes the responsibility to protect our cosmic oasis and to extend a hand of collaboration to all who share it. Galactic collisions are the universe's great forges, where gravity's slow dance compresses vast clouds of gas into brilliant firestorms of new stars. This violent process, observed across the deep time of cosmic history, enriches the cosmos with the very elements that build planets and life. We have seen how these stellar nurseries, like those in the Antennae galaxies, are born from chaos, and how their furious energy can both create the conditions for habitability and just as quickly snuff them out. These mergers are not rare catastrophes but fundamental chapters in the life story of galaxies, shaping everything from their structure to their ultimate fate. Our own existence is a direct legacy of such ancient cosmic encounters, which scattered the heavy elements that now form our world. Understanding this grand cycle connects us to the universe in the most profound way. It transforms the silent points of light above from a static display into a dynamic, evolving narrative. The next time you look up at the stars, remember you are witnessing an ongoing story of construction and rebirth, a saga written in starlight that continues to unfold across the eons. Our voyage through these colliding giants reveals a universe where creation and destruction are not opposites, but partners in a timeless dance. The violent birth of stars from galactic chaos humbles our brief human story, placing our lives within a narrative written in billions of years. We are living witnesses to a cosmos that is constantly rebuilding itself, where the end of one galactic structure marks the brilliant beginning of countless new suns. This perspective invites us to carry forward a sense of profound wonder, a recognition that the night sky is not a static painting, but a living, breathing entity. Every pinprick of light you see is a testament to the universe's relentless creativity, a sun born from ancient turmoil. I encourage you to step outside and look up with these new eyes. Share this cosmic story with a friend and let the immensity of it spark a conversation. If these journeys into the mysteries of space have captivated you, consider subscribing for more explorations into the infinite wonders above. The universe's story is still being written, and together we can continue to uncover